Hello guys, this is Rick from MathX, and today we'll be going over the number 25 from the AMC 8 of 2020. Now, this number 25 was astoundingly easy. Like, the number 25 from the 2019 test was just a simple application of a slightly advanced concept. But the 25 from this year's test, the 25 from the 2020 test, was actually even easier than that. It was a simple application of a simple concept. Most solutions you'll find online will give the solution to this problem in less than 3 or 4 lines, because that's just how easy this problem is. If you can just set up a simple system of equation, then this problem pretty much gets solved. But even then, this problem is ranked number 25th, and the diagram that they gave looks kinda scary. However, all this bravado is just overcompensating for the fact that this problem is really easy to solve. So, without any further ado, let's just get into this problem, and let me show you how it's so easy. Rectangles R1 and R2, and squares S1, S2, and S3 are shown below. And they combine to form a rectangle that is 3,322 units wide and 2,020 units high. What is the side length of S2 in units? Okay, so basically the problem gives us 2 rectangles and 3 squares. It gives us the dimensions of the larger rectangle formed by these 5 figures, and it's asking us to find out the side length of square S2. Okay, so the first thing that should stick out to you when solving this problem is the fact that it's asking you for a side length, and pretty much both the dimensions listed in the problem can be derived using all the side lengths shown in the problem. And from there, you should just begin to set up equations on how you derive each side length using the side lengths shown to you in the problem. So for now, let's completely ignore R1 and R2, as if you use them, it actually overcomplicates the problem. Right now, let's just look at squares S1, S2, and S3. So they use capital S1, capital S2, capital S3 to denote the squares themselves. But for our sake, let's represent the side lengths of each of these squares as lowercase s1, lowercase s2, and lowercase s3. So doing that, we see that lowercase s1 plus lowercase s2 plus lowercase s3, these 3 sides are equal to in length the long side of the rectangle. And we know that this long side of the rectangle is 3,322 units. So we can write this first equation. S1 plus S2 plus S3 is equal to 3,322. So this was pretty easy. How about trying to find out the short length of the rectangle using S1, S2, and S3? This may seem a little more complicated, as there is some overlap between S1, S2, and S3. However, let's just forget about that overlap. For now, let's just separate the 2020 side into 3 regions. This first region we can call S1 minus S2. The second region we'll just call S2. And the third region we'll call S3 minus S2. And how we got the side lengths based on S1, S2, and S3 should be pretty simple. The region above this line is just the side length of S1 minus the side length of S2. That's pretty simple. This region is just translating a side of S2 further to the left. These sides have the same length. It's just one's translated further to the left. And finally, this region below this line, we can just compute that value by just taking the total length of S3 and subtracting S2 from it. So we get that the sum of these three lengths should give us 2020. So S1 minus S2 plus S2 plus S3 minus S2 should equal to the shorter length of the rectangle, which we know to be 2020. So now we have a system of two equations, and we have three variables. So typically, when we would have two equations and three variables, we won't be able to solve for the values of the variables. But in this case, we're kind of dealing with something special. We see that in both equations, we have the same amount of S1s as S3s. We have one S1 and one S3 in the first equation, and we have one S1 and one S3 in the second equation. So we can actually cancel out all of the S1s and S3s by subtracting the second equation from the first equation. So doing that, we get that the S1s cancel out and the S3s cancel out. So basically, we're left with S2 minus S2, which is just the same as S2 plus S2. And then we subtract an S2 from there. And then we have another minus S2, so another plus S2. And of course, on the right-hand side, we have to subtract 3,322 and 2,020. So doing that, we would get 1,302. So simplifying the right-hand side of this equation, we get that one pair of S2 and minus S2 will cancel out. So in the end, we basically get 2S2 is equal to 1302. And just by simply dividing both sides by 2, we get S2 is equal to 651. Or answer choice A. Now, this video might take a little longer than you expect just because I'm showing you all the steps, but any experienced problem solver can instantly run through all of this and get you the right answer pretty simply. Pretty much the only challenge to this problem is developing the systems of equations for the 2020 side, as the systems of equations for the 3,322 side is pretty simple. You just add up S1, S2, S3. So this is just another important example of how important it is to be able to create equations and define variables and all that stuff. As this was an AMC 8 number 25 that one might think had a lot to do with geometry. However, in this problem, this was just another simple algebraic manipulation kind of problem, showing that if you really want to succeed on AMC 8s, you got to make sure that your elementary algebra, basic word problem skills, and basic equation forming skills are up to par. And by doing that, you should be able to solve most problems. So in the future, just do whatever problems you can. And remember your algebra, as this is the vital key on any AMC 8.